Yeah, Niranjan, am I audible?
Yeah, you are audible, sir. Can you enable your camera so that?
Okay, okay. Let me also means join with my actually another device.
Okay, okay. Take your 1 minute of time, sir. Not an issue.
Yeah, now am I audible? Okay, right, I think.
Yeah, you are audible, sir.
Okay, fine.
Shall we start?
Ah, yes, yes, sure, sure.
Okay. Yeah. Good afternoon, all the participants. So now we are going to begin our next session. That is session 13. And the topic for this session is future of computing with 2D TMD materials, innovation, prospects, and challenges. So let me introduce the speaker. Dr. Satish Chandra is working as an assistant professor at MNNIT Allahabad, Prayagraj. Before joining MNNIT, he was postdoctoral fellow at IIT Gandhinagar. Dr. Chandra has also worked as an assistant professor at Madan Mohan Malviya, University of Technology, Gorakhpur, India, from 2018 to 2021. He did his PhD and MTech from IIT Dhanbad, India in 2020 as well as 2015 respectively, and BTech from Dr. APJ Abdul Kalam Technical University, Lucknow in 2012. He is an expert in the field of condensed matter physics, photonics, and VLSI circuits, and published 35 referred SCI Thomson Reuters Index journals and international conference papers. Dr. Chandra had also been elected as the president of ASPI, a student chapter at IIT Dhanbad in 2018, and he was also the secretary in 2017. He is a senior member of IEEE and early career member of ASPI and OSA. Welcome to you all, sir. You can start sharing your screen and you can go ahead.
Yeah, okay, okay. Do we where the style screen? Somewhere it is coming entire screen or what?
No, your screen is not at all visual, sir. You need to save the screen.
Hmm, tap on the camera. No, not this one.
In the meantime, you can also enable your camera if possible.
Oh, oh, sure, sure, sure. Yeah. Okay. Niranjan, I'm getting that I want to share my entire screen. Is there any option?
So you
Uh,
just need to select your full screen, then only you will be able to save the screen.
I'm using my this tablet actually. So
Okay. So
uh,
the same option
start
is
now.
there. Yeah, now maybe it is coming. Let me see.
Yeah, okay,
Yeah,
fine, fine.
now it is visible, sir.
Mm. Okay, well,
Yeah, now it's
good
okay,
af-
fine. You can go ahead.
very good afternoon, and it's very glad having a great pleasure to be with here with you, and I'm very thankful to Niranjan and his team that he has invited me to give a lecture on the future of computing with it, 2MD and TMD materials. So before I'm going to start my this particular topic, so let me introduce myself that I have come. I'm from the Prayagraj. So basically nowadays you must be here and there. You're listening about the Mahakumbh and all. So basically, I'm from there. That very sanctum place that is MNIT. Okay, which is established in late 90s, and later on in 2005 it becomes basically MNIT. So here the basically the red point where you can reach it here, the place. I welcome you all to come here to be a part of Mahakumbh. So here I've shown a one picture here. Here. You can see it is a little bit visible about the Sangam. You can see it here, Ganga and Yamuna actually. So I come from this place. So nowadays there is a lot of rush is going on. So definitely if you are coming here, just be planned before at least minimum 15, and then you come. And definitely when you are coming and visit my college as well, you will feel a little bit well known about the what is the MNIT. So if I'm not going to exaggerate so much about the MNIT, because the MNIT is well known for their name, and which is the first university, or you can say institute, which basically run the computer science in the whole India actually. So that is what overview of the MNIT. Now comes to my topic. So why we required to know about the 2D and TMD materials basically. So as per why we know that day by day, what is happening, we want to that device should be more shorter, more miss, like it should come in our tip of the hand and all like that one. So there is a lot of problem which we are going to face in this one. So I feel like that 2D and TMD materials are one of the solution that gives us that whole basically problem which occurring in the that bulk materials basically. So that is one of the prospect which I want to look forward for the 2D and TMD material. So that is what topic which I'm going to cover up here. Definitely whatever we are making the analog circuit and all, that all basically depend on the material devices. So first of all, we need to understand what is the basic behind the 2D and TMD material. Then definitely we can able to understand how we can develop a different devices on the basis of 2D and TMD materials. So this is what I'm going to tell you over my throughout this lecture, that is what is the role of the 2D materials, or you can say TMD material, for the future aspects. And then I'm going to discuss what are the basic properties and structure of the material. Like mainly I'm going to focus on the graphene TMDs and the black phosphorus. And then further I'm going to tell what is basically 2D devices like transistor and tunnel FET, how we are basically designing. And then I'm going to tell you what are the basically challenges faces going to face during the 2D, and then what could be the better option to do all these things. So before I'm going to come into the bigger picture of 2D, first of all, we need to know what are the basically number of 2D or TMD materials are there. That is more than 140 2D materials are present over here. You can see it in the picture that you can see over from the insulator, semi-metal, metal superconductor, then semiconductors. There is a lot of range, which is basically nowadays up to 40, and it is still growing on, because continue the research is going on to just adopt this 2D material in the day-to-day lives, like what we are right now in the basically depending on the uh, silicon type of a devices basically. So these are covering the, if I'm going to look into the insulator is also there, that is a boron nitride, then semi metals are there, that is a carbon, silicon, and germanium. Likewise, go into further in the metal conductors, you will find out the VOS, TIS2, like that, different type of materials are there. Then further, if I'm going to look into the, nowadays that very much research is going on that MOS2, WS2, SNN2, because they're having another prospect of the basic material, because basically we do a doping in a case of when we are making some kind of PN junction type of material or like that one. We dope the system. But what we are finding in these MOS2 or you can say TMD materials, basically, we are finding out that MOS2, like that one, itself behaving like an N-type semiconductor. Like similarly, the WS2 is behaving like a P-type. I'm giving a one of example. So we need not to do a doping in this case of that one. So itself a material going to behave like a N-type or P-type. So that become a more advantageous. That's why that nowadays the research is more prevalent over this type of 2D material. And then 3-6 family of material, that is also one of the basic factor we look forward, because overall what we want to make a whole system with the help of 2D material. So that is what I want to share with you, all this thing, that how we can go and move towards the 2D material and TMD material rather than the silicon type of material which we are right now we're utilizing. So what are the promises we can do with this 2D and TMD material? Like nowadays the flexible type of electronics are going on. So you can see it here that watch we can make, likewise the plastic type of machineries we can develop, then MSB, likewise we can utilize that thing in the car system, mobile, everywhere we can use, wherever the basically that silicon type of a silicon based devices are basically used, we can utilize this type of a 2D and TMD material basically. So what is that? If you're going to look into the last 50 years, what we have seen, we are just doubling, as per we knows all that Moore's law says that every year what is going to have a doubling of the transistor is within the particular square meter, basically square centimeter is basically doubling that transistor. So what is that? If I'm going to look into now that what if I'm going to look into the Core i7, what is it saying? It is nearly 1.3 billions of basically a transistor within the area is basically there. That is what I mentioned also here, 1.3 billion transistor. Like you can say China within that 122 millimeters. That population of China is within that 122 millimeter square. That is there. So right now still we are growing towards the further, so that we can compress this device. Okay, to further we can reduce this size and all. Okay, so that we can further within a particular millimeter, or you can say number of transistor to be sinking down further. So what is that problem basically occurring? So if I'm going to look into this picture, if I will go the material which is having a below this particular region, if I'm going to look into this nanometer scale below this one, the Moore's law basically facing a lot of problem, which is when we are shrinking down this thing. So that is what the things we need to take care of that one when we are utilizing this bulk materials like a silicon and all. So that is what I'm going to discuss here first of all. So now comes to that one. So what is there basically if I'm going to shrink particularly one silicon type of a material device, or you can say a bulk material based devices, what is that we are facing actually? First of all, if I'm going to look into this is a nothing but a bulk material. If I'm going to cut a one bulk material, what is happening? There's a dangling bonds are coming. Due to the dangling bonds itself, there's a lot of reaction is going to come. Due to that one, we are facing some kind of issue. Okay, that is one of the problem in the bulk material. Later on, when we're going to shrink it down, what is then? First of all, that surface is scattering because of this dangling bond, and then we are facing a velocity saturation within this material basically. Velocity saturation because that length is basically sorted. So what is going to happen due to the electric field? It attain a maximum limit of the velocity of the electron, rather than what we want. It should not go early. It should not reach earlier that velocity saturation. That is occurring in the case of when we are sinking down this material, bulk material. So further, if I'm going to go into the further thinking down that one, what is going to happen due to the velocity distribution? There is a impact ionization will be there. So what is that? The second region is coming, that is impact ionization is coming. So due to the impact ionization, what is going to happen at the drain side? What is happening? There's a hot carrier effect is going to occur. There's a which is having a lot of energy. To do that, what is going to happen? That what the device is basically functioning properly, it is going to be deteriorated day by day. I mean, after a application of different higher electric potential, if I'm going to apply. Due to that one, what is going to happen? That high leakage current occur because of due to this hot carrier effect. Basically, these are the few major issues are occurring when we are going to use shortening down this bulk material basically. But what is there if I'm going to look into the 2D material? There is no dangling bonds. There's no dangling bonds in the 2D material. Due to that one, we can overcome this the problem of surface skating. This is the one of the best thing. Another is a ballistic type of a transportation is occurring within this 2D material. 2D that one, what is going to happen? That velocity saturation and some another kind of a problem which is occurring. That is I'm going to discuss later on this slide only. So if I'm going to look into this picture, this is our conventional type of a MOSFET. Okay, so I'm going to sinking down. What is going to happen? The electrostatic length. If I'm going to say length means this device having some kind of a length L. So definitely it's having an electrostatic length which is coming in between here. That will be lesser than this length. Okay, so we're having a scope of a small electrostatic length which basically prefer your conduction basically. So that is what we need to take care of that one. So transistor become more difficult to turn off as a gate dimension is basically shrinking. So that is going to overcome in the case of 2D material when you are going to utilize. That is what I'm going to make you sure about that one. So now what is going to happen when we are going to decrease down this electrostatic length? That is what that formula is given here. Okay. So if I'm going to say electrostatic length is like lambda, and I'm taking that the total length of the system is like 5 of lambda. Okay. So what is going to happen due to that one? There is a first of all the shortening of the channel is going to occur. Due to that one, DIBL, that is drain induced barrier lowering is occurring. Because of that one, it is not going to attain its original what we are getting right now. You can see it. That is going to be not attained. That is one of the things. And now, if I'm going to look into the different materials, that is silicon, germanium, and gallium arsenide, we can shrink it up to like maximum up to this one, that 0.18, 0.58, 0.74 correspondingly. That is less than 1 nanometer. Okay, and if occurring this thing, okay, that makes our the problem, that is DIBL. Okay, so we cannot overcome this problem when we are continuously going to utilize this bulk type of material. That is the one of the another problem which we are facing with the 3D materials, or you can say bulk material, which we are basically nowadays using in day-to-day life. Now comes to the prospect of the 2D material, that is ultra thin channel with a good mobility. So as you can see it here, the three lines I have shown, you can say four here, the black and this gallium arsenide, and this is a silicon. Okay, as we are reducing the length, as we are reducing the size of the device, what is going to happen? That its mobility is continuously decreasing for the even in the case of indium arsenide also. Okay, for the case of indium gallium arsenide in case. Okay, and this is for silicon. So overall, you can say for the bulk material or the 3D material is continuously going to decrease very sharply. But when I'm going to just take one example, that is MOS2. If I'm going to continuously shrinking down that device length, so what is going to happen? The mobility doesn't affect so much. Little bit only there is changes there. So that's why I'm saying that mobility is still there, almost like a constant. But in the case of bulk material, it is not attain the same thing. So that's why we can say that on the behalf of the mobility, we should definitely use this our 2D material for the case of MOSFET or FET, whatever we want to make a design. So now comes to the fundamental property of 2D material. So which basically defines you and tells you the what is the basically mobility of these different 2D materials, and application basis we can use a different type of 2D materials. So you can see it for the graphene, its mobility is near about 1000 to 1 lakh nearly centimeter square per volt second. Okay, but although there's a band gap having a zero, definitely there is some kind of advantage as well as there is a disadvantage of graphene having a band gap zero. Second, hexagonal boron nitride. Okay, it is a insulator, so that's why we can hear that there is no mobility. That's why because of the insulator there, it's having a band gap of nearly this thing 7.2 electron volt. That is indirect band gap. And now the TMD, that is MX2, where the M is basically metal and this is the axenes. So where you can say that M would be WMO likewise, which is we can use, and X is axene, that is X SE, that is sulfur, selenium, and tellurium. These are the things are there, and its band gap is going to become in the range of the band gap of the semiconductor, that is from 0.6 to 2.3 electron volt, depending on the layers which we use. Basically, if I'm going to talk about the TMs, basically it's in a natural way, it is occur in the pairs, basically pairs of the layers is occur in the natural format. And if I'm going to look in the mobility of this one, it is going to range from the 10 to 500 centimeter square per volt second. So basically, although there's a lot of difference between the graphene and the TMDs, but there's an advantage here because we have some kind of a band gap, so that we can have a switching ability here rather than the band gap in the case of graphene. And the last one is black phosphorus. If I'm going to look into the mono layer, it is having a 2 electron volt, and if I'm going to increase a few layers, then it is going to have a 0.3 electron volt, and it's having a range of 100 to 1000 centimeter square per volt second. That is what basically these are the basic material of the 2D, which basically can be a future aspect of our future computing. Basically, there are the pictures of the graphene, black phosphorus, and dichalcogenide, boron nitrates are given. Okay. So now comes to the what is this graphene? Basically, graphene, as per I know, so many of know of this thing. Since if I'm going to check about the band structure of this one, so conduction band minima and valence band maxima is basically it is in it at the tip of that one. Basically, they are touching at the tip of this one. So there is no band gap in between the conduction band and valence band. So there is a zero. It means if I am going to give a little bit of a potential, what is going to happen if the electron which is going to jump directly into this one? There's no any kind of a means controllability of the switching. That is what the problem with the graphene structure. So basically, 2 carbon atom per unit cell. Basically, if I'm going to talk about the more bigger picture of this one, so within a 1 unit cell, there is a only 2 carbons are there. Since they are overlapping to each other, and it is having a making a cones, so that's why it is having a massless fermions. That's why it is easy to move in the valence band and the conduction band now in a quicker way, and it is having a linear dispersion due to that one. So having a inversion symmetry, you can see it here. They are having a inversion symmetry. If I'm going to put a mirror here, it is basically follow up a mirror. So that's why the inversion symmetry is also there in a picture. If I'm going to go into the more details of the material aspect, you will understand what is basically inversion symmetry basically. So let's talk about only the band gap and the massless fermion. Due to that one, what is going to happen? There's a basically problem of the switching in this case of graphene. So because there's a very small type of a, no, it means small, I'm saying it is a zero band gap. Now comes to the 2D TMD material, that is transition metal dichalcogenide materials. I have taken a one of the example, that's MOS2 basically. So what you can see it here, if I'm going to see a band gap of that one layer, what is going to happen? This is a Fermi energy. Okay. So within this material, you can see it here. What is that? This is nothing but a valence band, and it is very close to the Fermi energy. So what is going to happen? It behaves like a N type of material or the P type of material. So what is that? It is an N type of material. Can anyone just tell me which type of material it is? Let it be more interactive, then it will be better that means to make you understand what is this TMD material, and we can, because this is the one of the material which is I'm focusing so much. Yeah, anyone just answer me this thing.
Hello, sir. Their some voice is muted, so that's why they cannot answer. They can only chat on the chat box. They can drop the message in the chat box.
Oh, okay.
It is mute.
Okay, sure.
Only when question answer will come, so they can raise the hand. Only after that they can talk. They can allow to talk. So
Oh,
as to participant, you can drop the message, whatever sir is asking. So you can drop the message so that we can communicate with him.
okay. Then it's okay. It's okay. Otherwise, it will be more disturbing when
What
you
is
open and
the
all.
more than 100 participants? So because of that, we have a control this voice. This mic we have control from our side only.
Okay. Okay, sure. It's okay. Fine. So that's why I also prefer to be in a physical mode.
Yes, sir. Actually, that's why
That
you are
is
not
only
able to get the answer. And
the.
because we have given the administrative power to our CCIT, so that's why they can
Mhm.
mics.
That's okay. Okay, fine. I got that. So basically, if you're going to see this one layer picture, okay, within this one picture, you can make a N type of P type material. You can say here the MOS2 is given, so it is behaving like a, since it is near to the Fermi level, so it behave like a what, P type of material basically. Is it a P type? I'm just missing that point. Is it a P type right material? I just miss out this thing.
Dear participant, you can drop message on chat box.
Once a time. Otherwise, I will tell
Yeah,
that it is.
please continue. Okay, no problem.
Yeah. Okay. No one has given the answer. Okay. Fine. So as you can see it here, it is P type. So further, if I'm going to layer down again, so what is going to happen? It is continuously going to change its property. So as per our requirement, we're going to modify this thing by layer, and what is going to happen? It's as you are going to increase the layers. What is that? The basically band gap also increases, and what is going to happen? It is shifting from a direct band gap to indirect band gap semiconductor. Okay. So as per we know, if you all are from the electronic backgrounds, and we know that what is the advantage of direct and indirect band gap. If I'm having a direct band gap semiconductor, we definitely use for the different type of LEDs type of a system, and for the case of indirect band gap semiconductor, we can use for the basically what we are using transistor BJT, whatever we are making. So So that is what the basically difference of these direct and indirect band gaps. So basically within this material we are getting a p type. So similarly different material like WS2 we can find out the n type of material likewise. So that is what the advantage here. As well as another thing, we are not having a zero band gap here. Although it is a 2D material like a graphene, but we don't have a zero kind of a band gap. So we can tune it accordingly by layer, and we have a switching capability also here. And another thing is there is a weak interlayer bonding, that is van der Waals forces are there. So van der Waals forces, we can say there's a no basically physical bonding, but there's an influence of that one, you can say. Okay? Simply like you can see it in the picture. It is basically layer by layer structure. So there's no direct linkage. So that's why it is a weaker interlayer bonding by van der Waals forces. That is what they are. And in a natural format, it is occurring like 2 layers only there. So if you want to grow further, you can grow on the basis of that one. Whatever you required on the basis of layer by layer structure. Now comes to the black phosphorus. That is a, you can see it here, black phosphorus. So what is that? In this one, you can find out there's a 0.3 electron volt for the bulk and for the 2 electron volt for the multi-layers here. It is a highly anisotropic effect in the mass of X and Y heavily. You can see it here in the case of, okay. So here also you can see bulk, direct band gap, tri-layer, bi-layer, and the mono layer. So here in this particular, what is that? This is the bulk phosphorus. There is no any kinds of changing from a direct to indirect band gap semiconductor. So as much as we can make a thicker, we can make. So there is no any kind of transition is occurring from a direct to indirect band gap of semiconductor. Okay. Now comes to the 2D electronics. So now we are using so many different means you can in your palm we are using nowadays this mobiles and all. So we are looking forward for these different material like rollable display and all. So nowadays you can see it here also that wearables. What is that? There's a graphene technology roadmap is there that which is given earlier. Okay, what is it is covering? Yes. How can I pause this? Excuse me. हेलो हाँ जी अब नीचे दे दो ना हाँ 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 77909030. Oh, sorry for the disturbance. Okay, this is a basically graphene technology roadmap, which is covering that flexible, rigid, and graphene touch panel and rollable display. Then graphene FETs like RF transistor, logic transistor, TFTs, and future devices based on that graphene. But although there's a lot of issues are coming across the graphene because it is having a zero band gap, as well as the switching problem with the case of when we are utilizing a graphene. Now, see graphene versus a bulk semiconductor. If I'm going to compare the bulk semiconductor with the graphene, what is going to happen? So definitely with the graphene, alone graphene we cannot use because it is having a zero. So that's why we need to basically dope it and then we can use it. Like a functionalized graphene, hydrogenated graphene, likewise, we can use it in a more suitable manner. Although right now I'm basically comparing with the graphene with the bulk semiconductors like a silicon. Silicon, you can see it here, the mobility is coming near about the 600 gallium arsenide having a more, that is 4,000 likewise. And if I'm going to look at the graphene, that is having a very much high, that is a 25,000 for the flake, and the for the epixel that is 3,000, and CVD it is getting a 2,000 nearly. Okay. And in the case of saturation velocity, what is there? It is in the range of 10 to the power 7 centimeter per second, that is coming to be 1 only. Comparatively, we are, if I'm going to look into the others, in the case of Indium INSB, we are getting 5 only, but in the case of graphene, we are getting almost like 8, which is a huge number for the electron saturation of the velocity saturation, you can say. So definitely in the beginning of that lecture, I've told you that in the 2D, basically we are having a ballistic type of a transportation. So we need to check about that one also, that is ballistic mean free path. That is here we are getting like 400, which is very much higher than the bulk semiconductor which we are using. So these are the advantages. So definitely we can use this advantage by just making a functionalized graphene, like we can dope with something like that. If I'm going to do functionalized graphene, we can use it in a different format of the, we can use the advantage of graphene as well as making a semiconductor. I have already having published a paper based on the functionalized graphene and all, that having a better opportunity of the band gap, which is getting nearly 0.2 electron volts. That is a good for the basically designing any kind of a transistor and all. So that is what I've explained it here. What is going to happen basically, if I'm going to look at the Dirac points, what is going to happen? So Dirac point going like this one, you can see it is going to empty very quickly, and similarly, if I'm going to go into this one, it attain very quickly that conduction band. So that due to that one, there's a poor on and off ratio will be there. So it is not good for the digital switching basically. So for the digital switching, definitely we need to do doping in the case of graphene FET, if I'm going to utilize in that one. So creating a band gap in a graphene, that is one of the things which we required in a 2D material when we are going to utilize. So basically in the nano ribbon, what we do basically, we like one of the example I've given, functionalized graphene. If I'm going to react with the fluorine, we are going to get that material. Likewise, you can see there is a number of that there. So likewise, we are going to get the structures. So this way, we can do the width variation and all, what means according to our required material dimension, we can do the variation in the width variation. As well as we can also grow the layer by layer the graphene also to make a more thicker one and all that. So now what is the choice of 2D material for the CMOS we should use? So here the graphene. Okay, graphene having a mobility which is very high. And in the case of black phosphorus, what is going to happen? What we are getting a continuous same kind of a band gap, that is a direct band gap. Okay, but there's a lot of opportunity in the case of TMD material, that is a transitional metal dichalcogenide material basically, where we have seen that for the case of MOST, we are getting a P type of material. And then similarly, if I'm going to look into the WS2, that is where that is occurring like a N type of material basically. So basically, if I'm going to look into the on-off ratio, definitely these two will be more better than the graphene material rather than. Okay. Now comes to the short channel MOSFET FET, MOS2 FET, that is having a good switching down to the 11 nanometer. If I go below the 10 nanometer, here we are getting more better means switching probability of that one. Rather in case of bulk material, below, if I'm going to go below the 10 nanometer, there is a problem in the there is a drain induced barring is occurring, and another short channel effect is going to occur. There's a surface scattering is there. There's a lot of problem which I have already discussed. So if I go below the 10 nanometer also, there's a lot of opportunity when we are going to use the MOS2. So since we know that graphene having a more mobility, okay, so we can do like this kind of a structure. We can distribute this channel within this channel. We can distribute in the format of graphene, MOSFET, and graphene. Although this is a very difficult to just have a bonding in between the MOSFET and MOS2, or you can say overlapping in between the MOSFET and MOS2. So very difficult task. But if we're able to design this thing, we can get a very good switching. Now comes to the issue of context. That is what I'm saying, the issue of context in between graphene and the MOS2 as well. There is a lot of problem. So if I'm going to check out the Schottky barrier and the Furby level pinning, what is going to happen? The current available in the RC for the TMDs and the black forest are still 2 order of magnitude higher than the silicon. So if I'm going to compare the silicon, which is going to have a less than 0.01. So if I'm going to say about the contact problem, we have not so much good in the 2MD material rather than we have achieved in the case of silicon type of MOSFET. Although we are getting 0.2 to 1.6 in the case of MOS2, for the case of WS2, we are attaining to 1.4 to 2 and 1.75 with the case of gold, graphene, and nickel and all. Okay, so that is the thing. That is what making the hurdle for the case of 2D material. That is a contract problem. And if I'm going to look into the requirement of ITRS, that is nearly 0.065 ohms millimeter. That is what the requirement is there. So that is what the challenge is still there in the case of 2D material, which if I want to make the transistors. Now comes to the MOSFET, making a MOSFET, a tunnel FET, then what is there? So with the case of silicon type of MOSFET, if I want to make a tunnel FET, what is going to happen? This is basically a conventional MOSFET. So for the making of tunnel FET, what we do? We basically do means make a 3 junction, but we basically deplete more N plus in between the below the gate region, and we try to make a the structure. If I'm going to look around the band structure, it should come like this one. Okay, so that what is going to happen? It should, when we are going to supply some kind of a potential energy, it should go above, so that this layer should be going to become in align with that one, so that there's a tunneling is going to happen. This 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 distance become lesser, and due to that one, if I'm going to apply some kind of potential, what is going to be? Rather going to do this, rather the electron going above that one, it will directly go into this part. So this is nothing but a tunnel phenomena. So this way we are going to make with the bulk type of a material. And which is can be easily means easily can be attained with the help of a 2D material. That is what that's why I've shown it here. Okay. Now comes to the what is there in the tunnel FET versus the MOSFET. So if I'm going to see that for the case of conventional MOSFET, we are getting this kind of a structure. Basically, there is a drain induced barrier lowering is occurring actually. But in case of when we are utilizing a tunnel FET, okay, what is that? This is what basically, this is a tunnel FET. Okay, here we are getting a good drain current, drain voltage. We don't have any kind of a lowering of the drain voltage. So due to that one, we basically prefer the tunnel FET over the conventional MOSFET. Okay, that is what it is showing. Now comes to the tunnel FET based on the TMDs. So what we are going to do, we penetrate this 2D material within the channel, okay, within the channel, and we are going to follow up what is going to occur. If I'm going to make with this one, what is going to happen? The different material we are having a different structure for the case of MOS2, MOTE2, WSE2, and WTE2. When we are going to penetrate this 2D material within this channel, and we are going to see that conduction of that one. So what is getting for the case of WTET, we are getting a better result for the case of this 2D materials. If I'm going to see it here, here we are getting into tunnel FET. Rather going to tunnel FET, we can attain it better with the 2D materials basically. As well as what we are going to attain here is a shorter in the device length. So that is what basically advantages over the tunnel FET also. We cannot constrain so much over the tunnel FET when we are going to make with the help of a silicon type of material or bulk material like gallium arsenide and all. So here as well as here we are getting below the 10 nanometer, as well as we are able to reduce the problem on the drain induced lowering. From the tunneling consideration, there is a direct band gap and a small mass of transport directional, as well as we are attaining a band gap of 0.6 electron volt. So these are the different material and over which we have a tabulated for the different material. It's a mobility as well as a effective mass of the electron as over the band gap. So basically effective mass is basically defining its mobility. So we need to look around the effective mass of the different materials of the 2D material. On the base of that one, definitely we have a different application oriented materials we can use. So you can see it here, here MOS2, MOSE2, MOTE2 cover different range of that bandwidth as well as the effective mass ratios. Okay, and for the black phosphorus, since we are getting a direct band gap, so we can have any as much as layers also. Here we are just summarizing the mono layer of the MOS2, MOSE2, MOTE2, WSE2. These all of these are there. So vertical tunnel FET. Vertical tunnel FET in the mean of what the mean of it? Let it be if I'm going to say some kind of a tunnel FET which is going to, you can see it here. This is basically vertical transport. Okay, if I'm going to look into this one, this is nothing but a vertical transport. As well as we can achieve the like if I'm going to say one example, let's say one material. This is a 2D material of N type and 2D material of P type. Okay, if I able to make this thing, we can even make a PN junction also. We can have a PN junction also, and if I want to make a BJT, what is going to happen? If I put a gate here, which is, you can see it here, although it is it is connected, we can make it a wonder wall also. So that is what the idea here, that we can make a vertical tunnel FET also here in the case of 2D material, which is very impossible in case of a bulk type of material. And what is the advantage of vertical tunnel FET is there? That is enhance the tunneling area and ultra short junction will be there. We can make a more thinner device when we are going to have a vertical tunnel FET. That is what the mean of what I want to tell you. Now comes to the 2D heterojunction vertical T FET. But 2D heterojunction means two type of different material we can use and have a vertical FET. So you can see it here, the picture which I've told you last slide. So if you are able to design this kind of thing, two materials, okay. So that's why it is called as a 2D heterojunction vertical T-FET. So if I'm going to look into the simulation aspect, we can see it here. So this is how we basically make a 2D heterojunction vertical T-FET. So vertical T-FET itself are basically more advantageous over the type of material. So these are the things which I have discussed. So what is that 2D material have a potential for the future electronics? Because the real and unique benefit of atomic thin body, because we are going below the 10 nanometer as well and attaining the solution for the drain induced lowering problem of the drain voltage. That is the important part. So another thing, so far the experimental studies have yet to demonstrate the full advantage and potential of 2D material for the electronic device. So that is the thing, because there is a very less experimental result has been available. So that's why I'm saying this part, that still we require a more clarity over this one. And then material sensitivity become a more problematic, because clipping of the one layer of, because the 2D material basically occurring in the pair. So layer means clipping out the one layer from a pair of the layers is also a very difficult task. So most 2D material are there in the bulk form, have extremely used in the industry application. And another, that is contact resistant doping schemes and gate stack option. So another thing is that, what is that contact resistance, which I have shown you there in the last in the previous slides. And another thing is, when you are going to utilize a 2D material, there's a problem of the doping, how we can do a dope. So because if I'm going to dope it, it is going to totally change its property. That is another problem. Although there is an advantage that the single material itself going to behave like an N-type or a P-type type of material. And third is gate stacking. What is that? If I'm going to develop a gate, if I'm going to make a transistor and I'm going to make a gate over that one, so there is also a problem of growing a gate over that particular channel. So that is what overall my talk on the future aspect of the computing. If you have any question, then ask me. And I'm basically working in the field of the DFT and theoretical study of 2D material, and as well as I'm working on the plasma oscillation theory of solids based on the non-linear property of material and current mode device and VLSI circuit. These are my topics. You can meet me for this one and have a discussion over the different topics which is mentioned on here. Yeah.
Yeah, thank you, sir, for a nice talk. So if any participants is having any kind of query, they can post it in the chat box, and then sir will give the answer one by one.
Okay.
Sir, in the meantime, I have one or two questions.
Which tool can be used for the black phosphorus? Okay, you can use a quantum ATK. Quantum ATK, I feel like that in the case of basically DFT, doing a DFT. Okay, the best tool for utilizing different type of molecular dynamics, you can use the quantum ATK. That is the best tool I've seen till now. Other than, there are so many different DFT based softwares are there.
Okay, so sir, how do you see this 2D materials transforming the development of this quantum computing or the spintronics devices?
That is what the aim, na? if I am able to make this transistor with the help of 2D material, we are attaining a mobility, higher mobility, as well as they are sinking down the device device length. So definitely, whatever you're going to make the computing, definitely that require a transistor. So if you have a better mobility, you have a better computing facility.
Okay. Okay. Fine.
Yeah,
And
I am
what is
using
cost
TCAD for the.
effectiveness for this 2D materials compared to the traditional semiconductor devices?
Yeah, repeat again. One.
What about the cost competitive for these 2D materials compared to the semiconductor materials
Uh,
for the commercial application?
yeah, that is means literally. I'm saying it is very difficult to say about the costing for this one because I have not also gone for the experimental result for the 2D materials. So for me, it is like little bit difficult to give you answer for what will be the cost for this one.
Okay, okay. So one more
I'm using
question is there in the chat box
I'm using TCAD
from
for that EMD and graphene. With respect to okay, okay, that is good one. Yeah, good. TCAD is also utilized for the device prospect. Good. Then with respect to the software for design of new transistor design, with respect to digital design, how could we progress like RFED and so on. Mm. With respect to the software design of a new transistor, I'm not able to understand with respect to digital design. Okay, digital design, no idea. I don't have idea for digital design. I am as per I know, I am working in the analog circuit and the materials domain, material characterization. So that will be better. You can ask those who is working in the digital domain, digital design domain, to enable to understand this black phosphorus. A black phosphorus is basically go into the that particular slide and then I will explain. Actually, I'm not getting what you want to understand by black. Want to understand for the black phosphorus. Black phosphorus, if I have just explained it here, like if you want to increase its layer, okay. Sometime what we need to do, uh, let it be. If I want to make a some MOS2 like that one, if I want to make more increase the mobility, or you can say if I want not so much mobility, then we can use a mono layer, then bi-layer, tri-layer likewise. Okay, but in all the different cases, we are getting only direct band gap semiconductor. That is the one constant thing which is continuously going. Is
the
the black
participants.
phosphorus the same as phosphorin? Not exactly. It is not exactly the same. Yeah, any other questions?
I think there are no questions on the chat box now.
Hmm.
Okay, so
Okay, nowadays the Mahakumbh is going on, so I definitely make you to means I just make you that you should come here and visit our college as well. So it is very near to the Sangam place actually, my college. So,
yeah, sure, sir.
hmm.
So now it's my great privilege to heartfelt gratitude for this insightful session on the
Good afternoon,
yeah.
sir.
Yeah,
Sir,
somebody
sir,
saying
I have one
something.
question, sir. Sir, you are talking about graphene. So the band gap of the graphene is you said that the band gap of the graphene is zero. So is that any kind of metal, or but it is made up of carbon? So it
No, there
cannot
is a
be that.
category of semi-metal actually. Okay.
Okay.
You cannot characterize as a metal, you cannot characterize a semiconductor. Okay, the graphene. Because graphene having a, it is touching each other, that the conduction band and valence band basically. It is
Oh,
basically like structure like this one. So due to that one, what is there? There's a zero massless fermion is there.
oh,
Okay, you cannot characterize into a metal in the semiconductor. Saying it is a metal, it's also a wrong. And saying it is a semiconductor, that is also a wrong thing.
okay, sir.
Uh, yeah.
Professor Amit Panda, do you have any query for the speaker?
Sir, in 3D IC, so what are the tools? Because Cadence, which are providing designing the 3D IC, but is still, I think, is not accessible to all the people. So, is there any other tools to simulate and 3D ICs?
3D ICs. Mm,
3D design. So for the all the device, 3D device, mm, multi-layer fabrication when you do. So mostly the design part is very difficult.
mm.
So in this case,
So actually, I'm also using Cadence and Quantum ATK. So I have also not looked for the other software. Miss, let me the other software. Mm. For what purpose you are saying? For the bulk type of material, if you
yeah,
want to
multi-layer
do.
design, if you 7-layer IC design, so when you do nowadays multi-stage layer fabrication
So
happens.
have you gone for the console? Means I have no idea, but check about the console if it there's a giving that kind of opportunity in the console.
Okay.
Maybe because I don't know about that one so much.
Okay, if the participants do not have any further questions, so let me thank the speaker for this session. So it is my great privilege to extend our gratitude for this insightful session on the future of computing with 2D TMD materials, innovation, prospects, and challenges. First and foremost, I would like to express my sincere thanks to our esteemed speaker, Dr. Satish, for sharing their profound insights on the transformative potential of 2D and TMD materials in the realm of computing. His expertise has not only deepened our understanding of the subjects, but has also inspired us to explore new horizons in this rapidly evolving field. As we navigate the challenges and opportunities for integrating 2D materials into advanced computing systems, gathering like these pave the way for groundbreaking advancement in technology. I would also like to acknowledge the participation of our audience who enriched the session with their curiosity and thoughtful questions. Your engagement ensures that the ideas discussed today in this session will spark future research, collaboration, and development. Once again, thank you all for being part of this crucial discussion. Thank you, Professor Satish Chandra, for this nice talk today. The participants are instructed to kindly join tomorrow's session, which will start at
Thank you,
11 p.m. with
Niranjan.
the
I'm
topic of
taking out.
AI/ML-based hardware accelerator for edge computing. So he's an industry expert from Qualcomm, lead design engineer, and I kindly request you to join at least 10 minutes before starting the session. Thank you, sir. Thanks once again.